That's very kind of you.
Well, thank you all for coming back.
Yeah, so we are happy to have Andy back for his last lecture. Please go ahead.
Right. So so what we've been talking about in the last few lectures is an old story, but kind of pretty story of starting from an n equals 2 supersymmetric d equals 4 quantum field theory and producing a complex integrable system. So this one, I don't know how to, so this is something happening in 4 dimensions with, so far we mostly talked about inserting local operators. So some picture like that, and it gets related to, by studying the low energy limit, it gets related to a complex integrable system, which is taking place in some completely other kind of internal moduli space geometry. And this B was the Coulomb branch. Coulomb branch of this 4-dimensional theory. And then a lot of what I said specifically in the example of the theory that I called T of SU2 and Triv. This is this specific theory that, sometimes also called just n equals 2 supersymmetric Yang-Mills with gauge group SU2. And then over here, the corresponding complex integrable system is supposed to be the periodic total lattice. For the group G equals SU2. And more generally, I could just put G on the left, and then I would also put just G on the right. Now, but this story is much more general. The picture is that for any n equals 2 supersymmetric field theory, you're supposed to get a complex integrable system. And in particular, we said this in words at various times, but let's just let's spell it out carefully. Given the data of C and G, or let's say the other way, G, a Lie algebra of ADE type, so simply Lace Lie algebra, and C, a Riemann surface, compact Riemann surface, there's another n equals 2 supersymmetric 4-dimensional field theory. We call T of G comma C. And so this is a somewhat newer story. I mean, the recent sort of interest in these theories is for like around the last decade or so. So they're called theories of class S. I guess it's not that new anymore. It's over a decade. But so this is a new family of n equals 2 supersymmetric quantum field theories, which and let me emphasize the picture of the world of n equals 2 theories somehow looks like this. There's Lagrangian field theories, and those are the ones that you get by the kind of procedure that I was sketching in the previous lectures, where you have some space of fields and you try to perform integrals over that space of fields. In particular, the data determining the theory is supposed to be fields in an action. And then there's well, okay, I don't know qualitatively how big the overlap should be. So maybe it's something like this. Here's the theories of class S. And then, here's all the n equals 2 theories. And the one that we've been talking about, our favorite example, the one that has to do with Donaldson theory, is sitting here. So that's the one that we called theory of SU2, triv. Well, if it's in class S, then it should also, yeah, maybe I should, why am I making it overly confusing by using the same letter for both things? Let's call the theory of class S, S of G, C. So the Lagrangian theory associated with the gauge group SU2 is also one of these theories of class S, where I take the Lie algebra to be A1, and now I take the surface to be CP1, but with, and now here's the secret that I didn't tell you before, is that we sometimes consider a surface with punctures and some additional data at the punctures. So with 2 so-called irregular punctures. And I think right now I won't try to be too sharp about what that means. So the data it's CP1, but plus a little bit of extra structure. So here we'll say with punctures and with puncture data. But in particular, you absolutely can consider the case where the surface is unpunctured, and that's a perfectly good case to start with. It just happens that in order to get this particular theory we've been talking about, we have to include some punctures. But there are tons of theories of class S that are not Lagrangian field theories, or at least believed to be not Lagrangian field theories. So like, for example, I could take here, probably the simplest one that I know is not Lagrangian, or that I believe is not Lagrangian, would be to take like SU3 and just a surface of genus 2. Or if I allow punctures, I can do something simpler. I can do SU3 CP1 with 3 regular punctures. Okay. And then why am I bringing up these theories of class S? It's because they provide a very nice examples for this business of the complex integrable system. So, oh, sorry, I used a T again when I should have used an S. I meant to call these S. The reason why I'm bringing these things up is for the theory, for the supersymmetric quantum field theory, S of GC, the corresponding complex integrable system is a rather famous one called the Hitchin system. Moduli space of Higgs bundles. And I'll write G Higgs bundles, and I won't be very precise about exactly which global form of the group you take. It's an interesting story, though. Ask me if you're interested. Over C. So, for example, well, okay, so I try to say what a G Higgs bundle is. So a G Higgs bundle is just a pair, E comma phi, where E is a principal. G, so G is some global form of this group. Holomorphic, so GC bundle over C, and phi is a holomorphic section of its adjoint bundle. Okay. So this is a rather, well-studied and well-loved complex integrable system, and they appear as the Seiberg-Witten geometries governing the low energy physics of this particular class of n equals 2 supersymmetric field theories. So if you ask what's the low energy physics of this theory, the answer is it's the Hitchins integrable system. Okay, now this integrable system, I drew for you this picture, and I told you some aspects of what it does in the physics. So what I said roughly was so the function tau on the Hitchin base, or in higher dimensional case, it would be like a matrix tau ij, giving the complex structure, so tau of u, given the complex structure of the torus fibers, mu, gives the low energy gauge coupling, or let's just say gives the low energy action of the theory of the n equals 2 theory. So now I'm back in general. I'm not talking about any specific example, but you might say that that's somehow less than satisfying. I mean, that's not really using this whole torus bundle. It's just using the function tau, the modulus of the torus. So you might ask me, what is the physical meaning of literally this torus bundle? Where does literally the torus bundle show up in the physics? Where do you see the torus fibers? And so let me tell you one answer to that question. So how does the full space M come to life in the physics? So not just this function tau of u, which is somehow derived from M, but how do you see the actual space M? Well, one answer to that question, and the one I understand best, is the following. Suppose we consider, so we have this 4-dimensional theory, and suppose we consider the theory reduced on a circle. So I have to say what that means. So we'll define a new 3D theory so what the 3D theory assigns to some 3-manifold, I guess I was calling my space times X, will be just what the 4D theory assigned to X cross a circle. So if I have a 4D theory, that's like a functor. I can plug into it, any kind of manifold. But in particular, if I only plug into it things which are of the form manifold cross a circle, then I get a function of X, and that function of X is a field theory 1 dimension down. So I only consider spacetimes of the form X cross S1. So then I get a 3-dimensional theory. Okay, so suppose I do that. And then we ask, what is that 3-dimensional theory? Well, in general, it's very complicated. It's as complicated as the original 4-dimensional theory. But we can ask the same kind of question that we asked in 4 dimensions, namely, does it admit a simpler description if you only ask about the correlation functions at long distances? So let's ask about the long distance description of Z3D. Well, then it turns out that it does have one, which is relatively pretty. So in 4 dimensions, remember, our description was in terms of U1 gauge fields plus a scalar which was mapping into the Coulomb branch B. The 3-dimensional description will actually not involve gauge fields at all. I mean, the reason is essentially that if you have U1 gauge fields in 3 dimensions, that's dual to a description just in terms of scalars. It's the analog of, in 4 dimensions, we had the electric-magnetic duality that said that a description in terms of gauge fields is dual to another description in terms of gauge fields. Analogous statement in 3 dimensions is the description in gauge fields is dual to a description in terms of scalars. So the upshot of that is that I'll be able to describe this thing without using any gauge fields at all, without using any G bundles, just using scalars. And what will that description look like? So kind of infrared quantum field theory, which is Lagrangian. It'll be Lagrangian. Given by an effective action. So it'll be like, again, some function, S from a field space to R, where now F bosons is the space of maps from our 3-dimensional spacetime, whatever it is, into M. So M, in other words, we had M, which was the which is this the total space of this complex integrable system, which appeared in some kind of shadowy form when you wanted to describe the 4-dimensional physics. M itself didn't appear, but somehow the tau derived from M appeared. But now, when you want to describe the 3-dimensional physics, literally this M appears. The 3-dimensional physics is literally a theory of maps from 3 manifolds into this M. And so I'm not, unfortunately, driving this statement for you. You could, okay, for people who thought about Lagrangians a little bit, you can derive this kind of picture just by taking the 4-dimensional effective action that I wrote and dimensionally reducing it on the circle, and you'll get an action of this form. But anyway, just to tell you what the story is, this is the story. And the action, so as usual, the thing that's easy to write is the bosonic part of the action. And what it looks like is just so if you have a map between 2 manifolds, if you have a map between 2 Riemannian manifolds, then there's a natural function associated to that map, which is the energy function. And that's what the action is here. So norm of d phi squared. So the critical points and the kind of classical solutions would be the harmonic maps. In general, we have this function, but to write it down, to write this norm down, we need a Riemannian metric on M. So what I'm saying is that when you take this quantum field theory, reduce it on a circle, the low energy effective field theory automatically produces for you a metric on M. The same thing happened in 4 dimensions, by the way. I didn't emphasize it at the time, but if we look at the effective action that I wrote in the 4-dimensional theory, coming back up here, the effective action that I wrote in 4-dimensional theory, if you looked at the scalar piece, so there we had a field A, which was a map into the Coulomb branch. And here, this part is a metric. This is a special Kähler metric. On B. In other words, literally the metric is of the form imaginary part of tau of A, dA squared. So the quantum field theory kind of automatically produces for you a metric. Here it's a metric on the base of the integrable system. But when you study the 3-dimensional theory, it produces for you a metric on the total space of the integrable system. And that metric, moreover, because of the amount of supersymmetry in the problem, you can prove that this metric has to be hyperkähler. So this compactification produces Riemannian metric on M, the total space of the integral system, which moreover is hyperkähler. Okay, let me say what, I don't assume everyone knows what hyperkähler means. So let me remind you what hyperkähler means. So definition, a Riemannian metric is hyperkähler if M, the manifold, admits complex structures. I'll call them I, J, and K. So this is one smooth manifold with 3 different complex structures. And I will be the one that we've talked about so far. So up till now, we've talked about this space as a holomorphic symplectic space. So, so we were describing it in one complex structure. That's complex structure I. But the kind of cool miracle about this space is that it doesn't only have that one complex structure. It has more. In particular, it has these 3 I, J, and K, which obey the quaternion relations. So Ij equals K, Jk equals I, Ki equals J, as well as, of course, they all square to -1 because they're complex structures. So these are also, by complex structure, what I mean is the endomorphism of the tangent bundle that gives the multiplication by I. So we call the space hypercomplex if it has those 3 complex structures, and then it's hyperkähler if this one single metric G is kähler with respect to all 3 of these complex structures. And so these are relatively kind of rare and unusual objects. I mean, so for example, saying that the space is hyperkähler implies in particular that that this metric is a Ricci flat metric, which means that's the solution of some complicated PDE. So these are relatively, they're not that easy to come by in some sense. But here in this situation of an n equals 2 supersymmetric field theory, we're supposed to, according to the physics, we're supposed to automatically get some hyperkähler space coming from it. And what I'm shooting for here is to explain how we use the physics to actually describe a little bit about this hyperkähler metric. But okay, so that's the picture. Now, okay, so maybe a little bit more of just general hyperkähler geometry before we give the description. So here's a little fact. If M comma G is hyperkähler, then, so I said it has these 3 complex structures, but in fact, it has even more complex structures. It has a whole CP1 worth of complex structures. So let's say, sorry, how do I want to say this? Well, let's just say it like this. So for any A, B, C in the 2-sphere, in other words, A squared plus B squared plus C squared equals 1, we can define I, A, B, C to be A times I plus B times J plus C times K. That's also a complex structure, an integrable complex structure, you can check. It's also a complex structure on MG. And G is kähler. for it. So we say, when you say hyperkähler, you first think of just having the three standard unit quaternions, but in fact, any unit quaternion gives you a complex structure on the space. And one of the big insights that's due to Hitchin about hyperkähler geometry is that it's a good idea to think of this S2 as actually being CP1. So in the way I described it, you know, I just described a point A, B, C in kind of real coordinates on the two sphere. So I described like a family of complex structures varying over the two sphere. But in fact, you can say much more. This family of complex structures, in a suitable sense, actually varies holomorphically over the two sphere, if I think of the two sphere as being CP1. And I guess one aspect of that is that you can build a twistor space Z of M. So given a hyperkähler manifold, I can put together all of its complex structures into a single complex space, which is fibered over CP1. So the total space is complex. The projection is holomorphic. Let's call this projection pi, and pi inverse of zeta is isomorphic to the space M with its complex structure I sub. So now I'll write zeta for a point of CP1 as a complex manifold. And then even a little more is true. So because mg is Kähler with respect to ijk, we have three symplectic forms, the three Kähler forms, call them omega I, omega j, and omega k. And so in each fixed complex structure, so for example, in complex structure I, the one we started with, we have the Kähler form omega I, and then we also have two more Kähler forms, two more symplectic forms, and those two symplectic forms get organized into the holomorphic symplectic structure. So holomorphic symplectic form var omega I, which is omega j plus I omega k. And so a similar thing happens in every one of these complex structures. You have this space, which on the one hand, it's Kähler, and so it has a real symplectic form corresponding to that, but also has two more real symplectic forms. And those two you organize into a holomorphic symplectic form. So in every complex structure, you have the Kähler form and the holomorphic symplectic form. So let me, because it'll be useful in a second, in complex structure I zeta, the holomorphic symplectic form var pi of zeta. So this is this family of holomorphic symplectic forms on this space, kind of CP1 family worth of them. And you can write them, of course, they're all determined by these three, omega I, omega j, and omega k, and they're determined in this kind of way. Where by omega plus and minus, I mean omega j plus or minus I omega k. So another way of thinking of this hyperkähler space is that it's just a C infinity manifold equipped with this one parameter family of holomorphic symplectic forms. And certainly if you know those holomorphic symplectic forms, you can recover the whole hyperkähler structure. So determining this omega of zeta, from that, you can determine the whole hyperkähler metric. Okay. Okay, that was that. So the last 10 minutes were just some kind of aside about generalities of hyperkähler geometry. The upshot is that hyperkähler metric sounds like a complicated thing, but what it's really equivalent to is essentially a CP1 family of holomorphic symplectic structures. Obeying some conditions, but in particular, if you somehow determine this CP1 family of holomorphic symplectic structures, then you've determined the hyperkähler metric. So now, what I want to explain is the kind of physics-inspired way of describing the hyperkähler metrics on these complex integrable systems. And I think I'll do it.
May I just ask a very quick
question?
Yeah.
Yes, please.
What happens with Hamiltonian structures? So if you have commuting Hamiltonians with respect to one Poisson bracket induced from your symplectic form, and now you start varying your symplectic forms, what happens?
Yes. Yeah, very good question. So, so certainly you having the integrable system structure in one complex structure does not mean you get an integrable system in the other complex structures.
Correct.
Yeah, I guess they do. I mean, yeah, what's the intelligent thing to say about this? Right, there should be some shadow of them in the other complex structures, but actually, I don't know anything quick to say about this.
No, but that's fine. I'm just yeah, this is fine. This is fine.
Okay.
I was just curious. I thought this was something obvious, but if it is not obvious, that's even better.
I don't think it's obvious. No, this structure is somehow it's a pretty non-trivial structure. Like just starting with the one integrable system.
Right.
It's not at all clear how you should deform it into the hyperkähler family.
Right. So in some sense, it's a question of integrability, because if something is integrable with respect to one symplectic or Poisson structure, then of course you have when we say that this is an integrable system, that means we specified which Poisson structure or which symplectic structure we are actually using.
Absolutely.
Yeah. Okay. Right.
Sorry. I just wanted to say something about this. I mean, there isn't an integrable system in a natural way in the J and K structures, right? But you can consider all of these at once. You can consider an object that interpolates between all of these things at once. The so-called, the Deligne-Hitchin moduli space, and is there an integrable system there that these descend from?
I don't think so. I mean, if there were, wouldn't it? Well, you say in some sense it doesn't restrict nicely to the. It doesn't restrict to the fibers.
Yeah, something that's on this big total space, but on only one of the fibers or two of the fibers, if you look at infinity, that you get subintegrable systems.
God, I feel like there should be something good to say about this.
Isn't the closest statement the actual statement about your coordinate systems, where you're saying that the Deligne-Hitchin systems for GL1 and for your group G are asymptotically equivalent? And we know that sort of asymptotically, this is relating them to the action angle coordinates, which are the integral system part, while at the local systems, we have the non-abelianization sort of fits together with that. I mean, I think that's the best statement there is.
Okay, you're saying that the statement that I'm about to say anyway is the statement that I should say. So maybe I'll just.
Yeah. You go ahead. I mean, sorry for derailing slightly. There was
no. It's a cool question. I've never exactly thought about it. Okay, let's maybe.
Let's just leave it.
Let's see what the structure is. So but okay, but since you asked this, let me try to put my finger on. So I'm about to describe a complicated construction, and you can lose sight of what's going on. But the maybe part of the point that I want to make is that given just the complex integrable system M, or if you like, given M and var pi sub I, which is omega j plus I omega k, right? That's the holomorphic symplectic form that I wrote a formula for before. You know, how hard is it how to produce the whole hyperkähler structure? And okay, so a priori it looks hard, but when you have in mind this physical picture, that what you're really doing is you're taking a four-dimensional field theory and you're compactifying it on a circle. In that picture, there's a sort of plausible guess for what's the extra ingredient you're going to need, and it turns out to be true. So the claim is we can do it using one more piece of data. One more piece of data that wasn't obviously present in the complex integrable system. And it's going to be, what is this? It's going to be a bunch of integers. Let me write it this way. It's going to be a function omega on the total space of my local system of lattices gamma. So I'll remind you, we had this Coulomb branch, and then over the Coulomb branch, we had a local system of lattices. So given a point U, we had a lattice gamma U, which varies in a locally constant fashion as you move around. And so we could make a function on the total space of that. So pragmatically, that's just a bunch of integers. Given any point U, any particular vacuum of my four-dimensional field theory, I have a bunch of integers. And this function is going to be, well, it's defined, it's a function taking values in the integers. So you would first think it's probably going to be like locally constant. In fact, it's going to be piecewise constant. So there's going to be places when it jumps. And the jumps obey some slightly elaborate formula called the Kontsevich-Soibelman wall crossing formula. We won't have time to say what that is, so that's a thing that that one can look up. But anyway, what I want to say is that you just need this one relatively small amount of data, just a bunch of integers, and then you can set up the following conjecture. So I'll first just tell you the conjecture, and then I'll try to say a little bit about what the physics kind of interpretation of the conjecture is. So the conjecture is that there exists holomorphic Darboux coordinates. So we want to describe this holomorphic symplectic structure, this family of holomorphic symplectic structures depending on a parameter zeta. And so it turns out that somehow the most convenient thing to do is not to describe them at some particular zeta, but to describe them at all zeta at once. So zeta was this coordinate keeping track of which complex structure we consider. So they're not just functions on M. So not usually you think coordinate system just means you give a bunch of functions on M, but because of this extra zeta parameter, it's functions on M cross C star. So it's going to be functions on M cross C star mapping into C star, labeled by lattice vectors gamma in gamma. What does holomorphic Darboux coordinates mean? It means that if you write omega of zeta, the holomorphic symplectic structure, you can write it as a sum from 1 up to the rank of gamma, dx gamma I over gamma I wedge dx gamma j over x gamma j times epsilon ij, where gamma I is a basis of the lattice and epsilon ij is the intersection pairing between gamma I and gamma j. Well, in my example, it was the intersection pairing. In general, in an n equals 2 supersymmetric field theory, there is always this pairing on the electromagnetic charge lattice called the Dirac pairing. But in the examples that come from Hitchin systems, there's always some kind of intersection pairing of cycles on the spectral curve. Okay, so I said there exist holomorphic Darboux coordinates, no big deal so far. But they're supposed to have some characteristics, and these characteristics are supposed to be strong enough to determine them. That's the dream. So the characteristic is, first of all, that as you take the parameter zeta goes to 0 or infinity, they have some characteristic asymptotics. So they have an essential singularity, but the essential singularity, you can completely characterize the behavior as you approach zeta goes to 0. So this is zeta goes to 0. So z gamma, so I'll remind you what these things are. So z gamma were the periods. Well, in our example, they were the periods. In general, z gamma were just some functions. In the kind of abstract setup, the z gamma are just some local coordinate functions on the Coulomb branch. They give the central charges of BPS states. But in our example, they were literally periods. So I guess I'll write that. And that's what would happen in every Hitchin system. These theta gammas were coordinates on the torus fiber. And this delta gamma is some pesky correction. I don't want to say much about it, except I'll say that it equals 0 at theta gamma equals 0. And if the most concrete version of this story, you should look at the section of this vibration that comes from taking theta gamma equals 0. So they have this kind of characteristic asymptotic behavior as you go toward the north pole of the twistor sphere. And then they have a kind of reality structure.
So is it really for zeta going to 0?
Yes.
Okay. Okay. All right. Okay. Good.
Zeta equals 0 is a very singular. Yeah. So maybe I should say just a little bit about what this hyperkähler structure is like, right? The picture is that at zeta equals 0, we're going back to this torus vibration.
Right.
Now, this torus vibration, of course, doesn't have a lot of holomorphic functions, right? Because it's, it has compact, complex fibers. So every holomorphic function on that guy is pulled back from the base. So to say that I have holomorphic Darboux coordinate functions on that space looks hopeless. And sure enough, the coordinates that I'm describing, they exist whenever zeta is not 0. They exist in all the other complex structures. But then something very bad has to happen to them when zeta goes to 0. And what happens is they have this essential singularity. So, right. I mean, the typical picture of this space is something that, algebraically speaking, it's affine for every zeta not equal to 0. And when zeta equals 0, it's this torus vibration. So those are the first two kind of basic properties, this asymptotic behavior and this this real structure. And if you just had those two properties, it would be easy to write down explicit functions with those properties. But now the third one, and the most interesting one, is that this function is piecewise smooth, or piecewise holomorphic, let's say. Holomorphic as a function of zeta. So in other words, hold the point of m fixed and just look at how it varies as a function of zeta. The statement is that it's piecewise holomorphic, and what it looks like in the zeta plane is something like this. It has these rays where it's discontinuous. And so it's holomorphic just in sectors.
But those sectors do not intersect at 0?
No, because the function has an essential singularity at 0.
Okay.
So I'm saying it's holomorphic. Certainly it's not
homomorphic. The sectors are emanating from 0.
Yes.
Okay. So I understand.
They're rays in the complex plane. Exactly.
Yeah.
And the jumps are of the form. So you could ask, given that the function is piecewise holomorphic, you could compare its values on the two sides. And the statement is that to compare the values on the two sides, they're related by this kind of universal automorphism of C star to the n, which looks like this. So what's going on here? So each one of these rays is associated with, let's say slightly more here. So with a jump of this form at the ray L mu, which by definition is the zetas in the complex plane, such that z mu over zeta, or let's say argument of zeta equals argument of minus z mu for mu in gamma. So the picture is we have this lattice, right? And for each lattice vector, we make some ray. We make a corresponding ray determined by the argument of the period of that particular lattice vector. And for each one of them, we have a kind of potential jumping behavior in the analytic structure of these functions. But then in fact, the jump might or might not occur, and that's controlled by whether this number omega of mu is 0 or not. So if all the omega of mu's are 0, then you have no jumps at all. Everything's just perfectly analytic. But when these omega of mu's are not 0, then they induce these kind of this jumping behavior of the functions.
Is it enough to reconstruct X using this property by some sort of factorization, Riemann-Hilbert factorization?
Right. So that's the big question, right?
Yeah.
Is this stuff enough to determine the function X?
Right.
So the conjecture is that yes, it is.
Oh, I see.
It has not been proved. It has not been proved morally because these jumps. So if you look at that jump, right? That jump is by some automorphism of C star to the n, right? C star to the whatever the rank of this lattice is. You can think of all the x's collectively as a map into C star to into that torus. And this jump is a kind of automorphism, birational automorphism of that torus. So what you have here is like a kind of Hilbert problem, but that's valued in this infinite dimensional group, which is the group of automorphisms of that torus.
Yeah.
And because, at least the reason why I have no hope of proving this is because I don't understand that group very well. Like, I think if it were a Lie group, then you would have a chance. I mean, similar things certainly have been proved. And I should say, I haven't given a lot of references, but for this part, this kind of Riemann-Hilbert problem in the finite dimensional case was tackled by, at least the place that I know, was tackled by Dubrovin and used by Chakotay-Vafa. That's a story about two-dimensional field theories. In this story, it's formally the same thing, but for an infinite dimensional group, but at least mathematically, it has not been tackled. On the other hand, you could be a pragmatic person and you could say, well, I don't care if there's a theorem, I'm just going to try to do it, right? So one thing you can do, so one can try to find such X gammas. Equation. So you can write down an integral equation, which if it had a solution would automatically have these properties. And you could try to do that just on a computer. And in some very simple situations, that has been done. And you can then you get some candidate for the hyperkähler metric, and then you can numerically compare it to the hyperkähler metric that well, these are examples where the system is a very simple Hitchin system, where you can actually calculate the Hitchin metric, and you can calculate the metric by this method, and you can just compare them numerically, and then they actually agree. So there's some evidence that this thing actually works, but there's no theorem. Anyway, okay, so what have I told you here? I gave you 3 lectures of basically physics, and then suddenly I gave you this construction. So let me just finish by trying to connect a little bit. I did it because I promised you some concrete construction. So this is a concrete construction. But now let me try to connect it a little bit to all that, to the physics a little more. I think the key thing, the interesting question that would come to your mind when you're looking at this thing is, what are these things X gamma, right? Like, why should these things exist? And so why? So the physics of these X gammas is supposed to be, so first of all, M, I said, is associated with the 3-dimensional quantum field theory that you get by taking your 4D theory and putting it on a circle. So M is itself a kind of Coulomb branch, but now it's a Coulomb branch of a 3-dimensional theory. I think since now we're in the world of Coulomb branches of 3-dimensional theories, I should try to say what's the relation to the other Coulomb branches of 3-dimensional theories, like the BFN kind of thing. And I think what I'm supposed to say is that this is the K theory version of BFN in some examples. I think those are the right words, but hopefully someone will correct me if I got it wrong. Anyway, it is the Coulomb branch of some quantum field theory. And then how do you get functions on Coulomb branches? Well, before, in the 4-dimensional context, I spent a long time telling you that one way you get functions on Coulomb branches is to take local operators, particularly local operators that are annihilated by Q, and compute their expectation values. And in 4 dimensions, the local operators were pretty simple. They came of well, in the Lagrangian field theories, they came from just taking the traces of powers of the scalar field. They were just determined by invariant polynomials. Here, again, we're going to take vacuum expectation values of local operators. So X gamma of zeta is the vacuum expectation value of a local operator, which I'll call, I guess, O gamma of zeta. O gamma of zeta is a local operator obtained from taking, so this 3D theory came from a 4D theory on the circle. So you could ask, where does the local operator come from? And where it comes from in the 4-dimensional theory is actually a line operator. So it comes from a line operator of the 4D n equals 2 theory, wrapped around the circle. So in other words, wrapped around the circle. Well, let's just say it like that. So in this functorial QFT language, if you have a 3D manifold with a insertion at a point that corresponds to a 4 manifold, which is the 3D manifold cross a circle with an insertion of the point cross a circle, that's a loop. So the thing that you could put on that is a line operator. And then more specifically, these particular line operators are the ones in the image of a kind of UV-IR map for line operators. A little, when I told you about the Seiberg-Witten theory, I told you that there's a UV-IR map for local operators that you used Witten theory. Here, to understand the properties of these functions x gamma, that comes from a very analogous thing, which is the study of a UV-IR map, but not for local operators, but for line operators. And then, so gamma, the last thing I'll say, gamma is electromagnetic charge, corresponds to well, the line operator, which is a an Abelian-Wilson-Tufte operator with electromagnetic charge. Gamma. And sorry, and the very last thing I should say is that the physics of the other key numbers that appeared were these integers, omega of gamma. And omega of gamma is a kind of BPS index, which counting BPS states in the Hilbert space, BPS states of charge gamma. In the Hilbert space of the four-dimensional theory. And then these jumps, so ultimately the most non-trivial ingredient in this story is this jumping property of the vacuum expectation values of the line operators. And that comes from some interaction between the line operators and the bulk BPS particles. Okay, I'm sorry. Well, I'm not sure if I'm sorry or not. Anyway, that's the story. So what I try to tell you is like some mathematical applications of n equals 2 supersymmetric field theory. And what I hope I convinced you is that n equals 2 supersymmetric field theories are connected to a surprising amount of mathematics. I only told you two examples. I told you on the one hand, the old story about Donaldson theory and Seiberg-Witten theory. And then I told you this new story, this newer story of BPS states and hyperkähler metrics. But there's many, many more things that going on in the world of n equals 2 theories. And so, so that's it. I'm done. Thanks.
Yeah, Andy, thank you very much for your nice lectures. Do you have time for questions, Andy?
Yes, if there are.
At least I definitely have one question.
Okay.
If you could give me some hint as to whether this business of holomorphic Darboux coordinates can be translated into something being done on a Hitchin system?
Yes, absolutely. So you could ask, in the case of the Hitchin system, what are these functions?
Yeah.
So very quick. I suppose so. What is concretely the Hitchin system as a hyperkähler manifold, right? So when I look at it in any of its complex structures other than the z equals 0 or infinity,
right,
you know that what it is, it's a moduli space of flat connections over the surface, right? Moduli space of complex flat connections over the surface. And so these x gammas, those are supposed to be some functions on the moduli space of flat connections over the surface.
Yeah.
And so you can ask just what functions are they, right? And the functions that they turn out to be are, well, let's talk in the simplest example. Let's talk in the case where the group is SU2. So you have connections for over rank 2 bundles. In that case, the functions that they turn out to be are the so-called Fock-Goncharov or cluster coordinates on moduli spaces of flat connections. Now that's in the, let's be simple. The simplest thing is the A1, but also with punctures. So let's be doing the punctured case. Then Fock and Goncharov have these coordinate systems on the moduli of flat connections that depend on the data of an ideal triangulation of the surface.
Mhm.
And so what's happening here is that as we move around in the Hitchin system, we're at each point of the Hitchin system, we're choosing some specific distinguished triangulation. And that triangulation gets determined by where you are on the base of the Hitchin system. There's kind of a decomposition of the base, where each region corresponds to a different triangulation of the Riemann surface. And then these X gammas are just the Fock-Goncharov coordinates associated to that triangulation.
So are you saying that actually in that case, one can solve almost explicitly that factorization problem that you were referring to?
Well, it's only, yeah. So in what sense is it explicit, right? So that's right. I mean, you can write a formula. You can say what the X gammas are, but it's not very explicit, because to really do it explicitly, right, you would have to solve the Hitchin equations.
I see. Okay.
So in fact, I would rather think of it the opposite way, that by solving this factorization problem, you can get around having to solve the Hitchin equations.
Okay, I understand. I see. Okay. No, thank you. Thank you. That clarifies my question. Yes, thank you.
Great.
If I can ask a question, you said that we should be able to see the X gammas as the expectation values of line operators.
Yes.
Why do we expect the expectation values of line operators to jump as you rotate zeta?
Right. So this is the tricky thing. So when I say a line operator, there's two different things that I could have meant. I could have meant a line operator which is defined in the original ultraviolet field theory. So that theory has some space of line operators, which let me call them the ultraviolet line operators. So for example, for the Hitchin system, for A1, those will be corresponding to isotopy classes of non-self-intersecting curves on the surface. And then there's the map that takes you from the UV to the IR. So for every UV line operator, when you sit at a particular point of the moduli space, it has some decomposition into kind of infrared line operators. And those are the simpler objects that are labeled by, these charges that I called gamma. Those correspond to loops not on the base surface, but on the spectral curve. And it's that map which has discontinuities. And in a sense that sorry, one more thing to say is that the notion of infrared line operator itself, so the map breaks down, but also the notion of infrared line operator itself breaks down when you reach these critical places.
So I guess I see the discontinuity as you move around in the Hitchin base.
Yeah.
I don't see the discontinuity as you change zeta.
Well, right. So okay. So one thing to say is just that this UV-IR map, zeta itself is a parameter. The line operator that you make depends on the parameter zeta.
Oh, right.
It's okay, yeah. That's the thing I should have said if I managed my time better. These line operators L gamma are really L gamma of zeta. And to write a formula for what the line operator looks like, it looks something like exponential of phi over zeta plus, in the abelian case, it literally would be this. It's like the integral over some loop. It's a supersymmetric version of the usual Wilson operator. The Wilson operator would just be this. We supersymmetrize it by adding the scalar. In doing that, we introduce this dependence on the parameter zeta. So that line operator is supersymmetric with respect to different supersymmetries depending on which zeta you take. And that's related to the fact that it's holomorphic in complex structure zeta.
Thanks.
Great.
So about what you just said, would it be accurate to say then that like if you consider the RG flow from your UV fixed point to your IR fixed point, like what is it? The zeta like parameterizes different flows, and then as zeta changes, you jump to a different IR fixed point?
I guess that's true if you think of if when you talk about a flow, you're thinking of the flow as not as the flow of this kind of combined system, which is the 4-dimensional field theory plus the line defect.
Mm-hmm.
Then I think that's right. I mean, as you change zeta, you're changing the line defect, and that changes the whole flow. And indeed, there's some critical phenomenon where the flow is kind of bifurcating at these critical values of zeta.
Okay, great. Thank you.
I had a simple question about just a thing that you maybe said in passing during the talk. I think someone asked about integrable systems and other complex structures, or like how it all changes as you rotate the complex structure.
Right.
And I think someone else said quickly that there isn't an integrable system in the other complex structures. I just want to make sure that's correct.
Sometimes there accidentally is one, but it's not related to this one, right? Like sometimes there is, like for the pure SU2 theory, there is, right? Because you have the Wilson line.
Well, yeah. So I would want the Wilson lines to be the thing, like in a generic complex structure, I would want the Wilson lines to parameterize to be the Hamiltonians.
Right. Right. So sometimes there is that other integrable system, but I think that's not related to the one that we're talking about here.
Yeah, I would agree that. I mean, yeah, that there's integrable systems on other fibers. I mean, for other complex structures sometimes, but I'm not sure that there's a solid connection between these other integrable systems and the one at the central fiber, the one in the Hitchin system.
Yeah. Also, Dima Irinkin's thesis can be seen as talking about how can you deform the integrable system structure, and for a certain, formalization of this statement, the answer is you can only do it in a formal neighborhood of zeta equals 0 in the Deligne-Hitchin space.
Okay.
Only in a formal neighborhood because of the Stokes phenomenon?
Yes, that's precise. So it's precisely the same in the 2D case. This is the statement that you can diagonalize, any regular differential equation formally, but non-formally you can only give that splitting on sectors. And but then this is precisely what we're seeing in these in the coordinates that you give. They're defined on sectors.
Well, I agree with that, but what would you have said? Okay, suppose the group was U1, then you wouldn't have had these jumps.
So I mean, I'm assuming that I'm dealing with a non-diagonal, non-abelian group.
Okay. What confuses me is just that even for U1, I don't see how to extend the integrable system. There, the other fibers are C star cross C star.
Which is. I mean, the C star times C star thing seems to be what you actually get in the other complex structures, right? Like it's okay to have the base C star. It's a sort of a trigonometric system.
Right, but it's not naturally C star cross C star. You have to choose one is the electric and one is the magnetic, whereas the other one is totally canonical.
So I mean, I think that this is why we don't quite want to say that we actually have an integrable system, but rather we have a relationship between the Deligne-Simpson twistor spaces, which asymptotically in the Hitchin base preserves twistor sections. And that really explains why the natural way to view the natural way that to view the 2D the natural way to view these coordinates is actually as a map from the local systems on the spectral cover to like the, GL2 or GLN local systems. So it's not quite some sort of global, it's a relationship between the abelian and non-abelian Deligne-Simpson spaces, not some sort of global actual integrable system map. As I understand it.
That sounds right to me. Whatever that's worth. Okay, well, thanks so much. This has been a lot of fun.
Well, thank you so much, Andy. This was fantastic. We really enjoyed your talks. Thank you very much. Yeah.
So yeah, I better go.
Yeah, you have another meeting to get to.
Yeah. See you guys. See you, everyone.
Take care.